Hi, this is Alex from devstories.eu. PyTorch Fundamentals, episode 10 of 18. If you stack 100 neural network layers together without one specific mathematical trick, the whole network mathematically collapses into a single straight line. The culprit is linear algebra, and the fix requires understanding linear layers and activations. A neural network is fundamentally a sequence of mathematical operations on tensors. The most common operation is the linear layer, defined in PyTorch as nn.Linear. This module applies an affine transformation to incoming data. It holds two internal tensors that it learns over time, the weights and the biases. When data passes through, the layer multiplies the input by the weight matrix and adds the bias term to shift the result and outputs 512 new numbers. During training, PyTorch continuously updates these weights and biases. They form the actual memory of your model. You might assume a deep neural network is just a long sequence of these linear layers stacked back to back. This is the part that matters. If you chain multiple nn.Linear operations together without anything in between, the math simplifies. Matrix A multiplied by matrix B is just another matrix, C. Stacking 10 linear layers has the exact same mathematical capacity as calculating one single linear layer. Your deep network is reduced to a flat linear equation, completely incapable of learning complex real-world patterns. To stop this mathematical collapse, you introduce a nonlinearity immediately after the linear layer. These are called activation functions. The most widely used activation in PyTorch is nn.ReLU, which stands for Rectified Linear Unit. After the linear layer calculates its 512 outputs, you pass that tensor directly into a ReLU function. The logic of ReLU is brutally simple. It looks at each number in the tensor. If a number is less than 0, ReLU changes it to exactly 0. If a number is 0 or positive, ReLU leaves it entirely alone. That single kink at 0 destroys the linearity. It prevents the next linear layer from mathematically merging with the previous one. By forcing negative values to 0, ReLU also creates sparse representations. This means only a specific subset of neurons activate for any given input, making the network highly efficient. The data flow is consistent. Your flattened image goes into the linear layer, gets transformed by the weights and biases, and then hits the ReLU activation, where the negative outputs are stripped away. You can then safely pass this activated tensor into a second linear layer to extract deeper, more abstract patterns. A linear layer determines how much mathematical importance to give each input, but the activation function gives the network the actual geometry required to learn the unpredictable shapes of real data. Thanks for spending a few minutes with me. Until next time, take it easy.